So our next speaker will be, and thanks for the talk again. It was very nice to have you here. And so our next speaker will be Antoine Bédard. I hope I not mispronounce it, from the University of Montréal.
It's good. It's good.
And who will talk us about the element. I think it's about the spectral evolution in white dwarfs, which is, I think, is the main topic. So okay, so please go on.
Okay. Thank you, Marcelo. Hello, everyone. First of all, I would like to thank the organizers for giving me this opportunity to speak and share the work I've been doing during my PhD. And so today I'm going to talk about the spectral evolution of white dwarfs, which is my main focus. And I'm going to talk about spectral evolution from a modeling perspective. And I'm going to show you how we can use evolutionary models, which include element transport, to simulate this phenomenon. The term spectral evolution refers to the fact that white dwarfs can experience radical changes of surface composition as they cool. And these changes are caused by several processes such as diffusion, convection, and mass loss or accretion. And one of the most significant evidence of spectral evolution is the fact that the fraction of white dwarfs with a helium-rich atmosphere changes along the cooling sequence. So, for example, here at very high temperatures, you can see that the fraction of helium-rich white dwarfs gradually decreases, reaches a minimum in the so-called dB gap, and then re-increases at low temperature. So what we think happens is that hot helium-rich white dwarfs have a small amount of residual hydrogen diluted in their envelope, and with time, this hydrogen diffuses upward under the influence of gravitational settling, and eventually forms a thin hydrogen layer at the surface. So at this temperature, we see a hydrogen-rich atmosphere. But then at lower temperatures, a convection zone appears in the surface hydrogen layer and eventually reaches the underlying helium layer. So the surface hydrogen ends up fully mixed in the helium envelope. So at this temperature, we see once again a helium-rich atmosphere. Another evidence of spectral evolution is the carbon abundance pattern of helium-rich white dwarf along the cooling sequence. So in the zoo of carbon-polluted white dwarfs, we have several types of objects. First, there are the PG 1159 stars, which are extremely hot and extremely carbon-rich. They have typical mass fraction of about 0.5. We also have the DO white dwarfs, which are cooler and sometimes show carbon with smaller mass fractions. And at much lower temperatures, we have the well-known DQ white dwarfs, which have helium-rich atmospheres with very small traces of carbon. And the DQs show a very interesting carbon abundance pattern, which is shown here on the right. So they form this very tight sequence of decreasing carbon abundance as a function of effective temperature, with decreasing effective temperature. And by the way, in my talk, I'm only going to talk about the classical normal mass DQs. I'm not going to talk about the so-called hot DQs and warm DQs, which are shown here as small dots. These objects are much more massive and much more carbon-rich, and we believe that they are produced by mergers, so they are completely different from the classical DQs, and I'm only going to talk about those today. So it's quite natural to think that these three types of objects are related, and the usual explanation is that a PG 1159 can turn into a DO and then into a pure helium DB, simply because the carbon sinks out of the atmosphere. But then at lower temperature, the carbon is brought back to the surface by the helium convection zone, so this produces a DQ. So these spectral evolution scenarios that I've just described are fairly well understood qualitatively, but we must also be able to test them quantitatively if you want to check that they are correct. So for example, we should be able with our models to evolve a PG 1159 star into a DQ star at lower temperature, which follows the correct abundance pattern. And we should also be able to model this helium to hydrogen to helium transformation that I talked about. So the goal of my talk is to show you that we are able to do so and that we can obtain very interesting results from this modeling. So the simulations that I'm going to present today were produced with STELUM, which is the new version of the Montreal Stellar Evolution Code. And I don't want to go into too much details about the code, but there are two things worth saying. The first thing is that STELUM produces complete stellar models from the center to the surface, which is necessary because we want to follow both the cooling of the star and composition changes at the surface. And the second thing is that STELUM includes a wide range of physical processes which cause element transport. And these mechanisms are fully coupled to the evolution. So here's a list of the transport mechanisms included. We have the 3 types of atomic diffusion. We also have various types of mixing, the most important ones being mixing by convection zone and by overshoot beyond a convective boundary. We can also include mass loss through a stellar wind or mass accretion. If you are interested in the details, I'm currently writing a paper which will feature a full description of the code. So the first simulation that I want to present is a simulation of this spectral evolution channel, which involves the helium-rich white dwarfs showing traces of carbon. And this is often called the PG 1159 DO-DB DQ evolutionary channel. So first, a bit of information about the parameters that I used for the simulation. So I started from a very hot 0.6 solar mass star with an initial envelope composition, which is a mix of helium, carbon, and oxygen, which is typical of PG 1159 stars. The envelope is 1% of the mass of the star, and the transport processes included are the 3 types of diffusion: convective mixing, overshoot mixing, and finally a weak stellar wind at high effective temperature. And here I just want to add something. The overshoot mixing, the extent of overshoot mixing is controlled by this free parameter FOV, for which we use a value of 0.05. And so this is going to be important later in my talk. So what you see here on the right is basically the chemical profile of the initial model. So on the y-axis, you have the log of the mass fraction of the various elements. And the x-axis is a measure of depth into the star. So basically this quantity Q represents the fraction of the mass above a given point. So for example, log Q equals -4 means that there is 10 to the -4 of the mass of the star above this point, or on the right of this plot, if you prefer. So this here is the surface. This represents the envelope. And underneath here, we have the carbon-oxygen core. And now I'm going to show you the simulation in the form of a small video, which shows snapshots of the chemical profile as the star cools. So first, the gravitational settling causes the carbon and oxygen to sink into the star. So the PG 1159 becomes a pure helium DB white dwarf. And then this dashed line shows the base of the helium convection zone, which goes deeper and deeper in the star as the star cools, and eventually reaches this carbon-rich layer. So carbon is dredged up and fully mixed in the convection zone. And as the convection zone goes deeper, the surface carbon abundance increases. But then the convection zone reaches its maximum depth, so the surface carbon abundance starts to decrease. because carbon sinks out of the convection zone here. And here you can see that the region in which carbon is fully mixed actually extends slightly deeper than the formal boundary of the convection zone because of convective overshoot. Oops. Okay, now what we can do is we can compare the predicted carbon abundance as a function of effective temperature to the observed abundance pattern of DQ stars. So this is shown here in this plot. This is the same plot I showed earlier, but with the red line showing the prediction from our simulation. So you can see that our simulation does a pretty good job of reproducing the observations, especially the first half of the sequence. Unfortunately, right now, we cannot extend our simulation to lower temperatures for a purely technical reason, which is that the radiative opacity for carbon is taken from OPAL, and the OPAL tables don't cover these low temperature. But still, this is a pretty nice result. And actually, the location of this curve in this diagram depends on several key model parameters. So first, it depends on the stellar mass, because the mass influences both the depth of the convection zone at a given temperature and also influences the efficiency of carbon settling, which controls the location of this carbon diffusion tail at a given temperature. Also, obviously, the carbon abundance pattern depends on the initial distribution of carbon in the PG 1159 progenitor, and this is controlled by two parameters, which are the carbon mass fraction in the envelope and the depth of the envelope. And finally, another parameter which influences the result is the extent of the overshoot region, which is shown here in gray. And this is controlled by this parameter FOV, which I mentioned briefly earlier. So just to give you an idea, the physical meaning of this parameter is that F times the pressure scale height gives the E-folding distance for the overshoot mixing coefficient. So F equals 0 means no overshoot, and F equals 1 means that overshoot mixing decays with E-folding distance of 1 pressure scale height. So we have basically four parameters that we can vary and see what their effect is on the results. So here these plots show the effect of changing the stellar mass, the initial carbon mass fraction, and the envelope mass on the predicted carbon abundance. And in each plot, I'm varying only one parameter while keeping all the other parameters fixed. So I don't have the time to go into the detail of these plots, but the important point is that all three parameters have a huge effect, and this effect is obviously degenerate. And what this tells us is that the DQ white dwarfs form a very, very homogeneous population, because if you had, say, a range in envelope masses, we would not observe such a tight sequence in this diagram. There's one parameter that I want to discuss a bit more, and it's this F factor, which controls the extent of overshoot. And the reason I want to discuss it more is that, unlike the other parameters, this one is very poorly constrained. There are 3D simulations, hydrodynamic simulations by the Warwick group, for example, that predict that F should be of the order of unity. But these simulations are currently limited only to shallow convection zones near the surface. So just to give you an idea, the 3D simulations are currently restricted to this region here, while carbon dredge-up occurs somewhere around here, so in much deeper layers. And there are reasons to believe that overshoot is less efficient for deep convection zones. So for example, in models of post-AGB stars, F needs to be 100 times smaller match the observations. For cool white dwarfs with deep convection zones, we have basically no constraint on the value of F. It could be anywhere between 0 and 1. It's a huge uncertainty for the models. But fortunately, our simulations, coupled with the observations of BQ stars, allow us to calibrate the extent of overshoot. So if we make the most reasonable assumptions for the other parameters, such as a 0.6 solar mass star and so on, yes, we can calibrate the value of F. So this plot shows the effect of changing F while keeping all other parameters fixed. And the green line is for 0 overshoot. The red line is our reference simulation with F of 0.05. And the blue line is with overshoot, a very efficient overshoot, as in the 3D simulation. So you can see that the abundance pattern of DQ white dwarfs can only be reproduced with a moderate overshoot efficiency of about 0.05. And this is a nice result because it's the first time that we have an idea of the amount of overshoot in cool white dwarfs with deep convection zones, which are currently inaccessible to 3D simulations. So, and it's important not only for spectral evolution, but also, for example, for accretion studies, because by changing the amount of overshoot, we change the mass in which the accreted material is expected to be mixed. And now for the last part of my talk, I want to come back to this, to the first spectral evolution channel that I talked about, which is this helium-rich to hydrogen-rich to helium-rich transformation. And this is what I call the DO-DA-DC evolutionary channel. And this transformation has never been really modeled before, at least not in a fully self-consistent way, because it turns out to be a numerical nightmare. You'll see why in a bit. So for this simulation, the setup is almost identical as before. The only thing that I change is the initial envelope composition. So instead of starting from a PG 1159 type composition, simply started from an almost pure helium envelope with a small trace of hydrogen, which is 10 to the -4 here. And now I'm going to show you how this chemical profile evolves. So first, the hydrogen floats up as expected, and the atmosphere turns from helium-rich to hydrogen-rich at about 45,000 Kelvin. So we now have a DA star. And then not much happens here. The star reaches diffusive equilibrium, but then at lower temperature, the hydrogen convection zone appears and reaches into the underlying helium envelope. And so both layers mix, and the surface hydrogen ends up fully mixed into the whole helium envelope. So at low temperature, this is now a DC star, because this amount of hydrogen is invisible at such a low temperature. And so that's it for this calculation. But now I want to back up a little bit and show you the last part of the simulation one more time. But this time I want you to focus on the effective temperature and the cooling age during the mixing process. So you'll see that during the mixing, the cooling age remains essentially constant. And second thing, the effective temperature actually increases during the mixing process. And this is caused by the change in opacity in the envelope. So it's pretty cool, because we are used to think that the temperature can only decrease during the evolution of a white dwarf, but that's not quite the case for a white dwarf that experiences a convective mixing. And the reason why the cooling age remains constant is simply that this transformation happens on an extremely short time scale. So just to give you an idea, during the mixing, the time step between two successive models is a few weeks, approximately. So that's why this kind of calculation is very challenging. It's because on one hand, you have an evolutionary timescale, which is tens of millions of years. And on the other hand, you have the timescale of element transport, which is less than a year. So that's very hard to handle numerically. So that's it about that. Now a short summary. So we are able to produce detailed simulations of element transport in white dwarfs, which allows us to model their spectral evolution. Applying these simulations to the PG 1159 DO-DB-DQ evolutionary channel, we obtain a few interesting results. The most important ones, in my opinion, being that we can provide a tight constraint on the extent of overshoot in cool white dwarfs. And finally, we have calculated for the first time a simulation of this helium-rich to hydrogen-rich to helium-rich transformation in white dwarfs, and we have yet to explore the parameter space of such simulations. So thank you for listening. I'll be happy to answer your questions.
Okay, thank you for the talk. So now let's go to for the questions. And okay, so let's see, because I think there are a lot of people talking in the chat, and so I'm missing some of them. Okay, so no, this is already from the previous one. So here someone asks, Shane Pratt asks about if you have compare your models with MESA models. Are you that to that question, whether you have compared that with the Althaus 2005 paper who explored that particular scenario, the first one, the transition? So have you compared your models with let's say full stellar evolutionary models, and how do they they compare the?
No, I haven't done that. I'm starting from I believe the question is about the initial chemical profile that I use, which is a simple version of full evolutionary calculations. But no, I haven't compared. But the initial chemical profile is quite close to what we expect from full evolutionary calculations from the main sequence. Yeah.
So here Tomas asks regarding whether there is some observational selection or some issue which explains why we have this tight clustering of the carbon abundance versus effective temperature. Yeah.
Yes. Let me go back to here. Here there are no biases, but underneath here, I think the carbon visibility limit is somewhere here. So maybe there are objects that we don't, DQs that we simply don't see here, that we don't detect the carbon. But at least, for example, we can still say that there cannot be a very large amount of overshoot, because we would observe DQs here if it were the case. Yeah.
Okay, so now we have a very interesting question from Nicole, in fact, that is regarding that some helium subdwarfs and also like these extreme helium stars or Arcor bores show some carbon in their envelopes, and they will evolve into DOs. I mean, we know that, but do you rule out that these stars will ever become like DQs because you find this tight population? I guess that's the point. Huh?
I'm not sure I understand the question, but what is the carbon abundance?
They show a carbon abundance of about 2% in the atmosphere. Would that be enough to turn them into DQs at some point in their life?
I think not, because if you look at this plot, if you put 2% of carbon in the initial model, the curve is going to be somewhere here. And this is way below the visibility limit of carbon in this range, I think, at least in the optical.
Okay, so now Evan Bauer asks regarding, okay, this is another interesting point, is whether there is some nuclear burning included in the models, because like
No.
when diffusion goes so deep inside the star, then it might destroy some of the hydrogen.
Yeah. There's no nuclear burning, but in my initial models, the hydrogen profile is stops here at my log Q equals -4 because here it would burn. So yeah, I don't include nuclear burnings, but my initial chemical profile takes that into account.
Yes,
takes
but
into account the fact that,
but diffusion will make it go deeper afterwards. Huh?
yeah, it's true, but no, it's not included in the calculation. Yeah.
Good. And so I think we are almost done, but I want to comment on one of the things, because you were comparing the F value of the overshooting. You were comparing different, different people that obtain different values, and you were saying that you can calibrate this F value of the overshooting. I'll tell you to be careful about that, because in principle you are not really calibrating the F value, because when you are using this diffusive overshooting, you have to use also a cutoff, because at some point you have to say, below this cutoff, I'm not, what you are really constraining is the extension of the overshooting region. But the mixing is almost homogeneous, is almost instantaneous, so because these timescales are very fast. So what you are really constraining is the two things at the same time, is where you put your cutoff for the exponential decay, where you say overshooting is not effective anymore, and the F value, because it's not any of them alone that you are constraining. This is something usually people forget when they quote this diffusive overshooting, that it's not only the F value, but the F value and the cutoff.
Well, my understanding is that we don't have a cutoff. We simply the overshoot coefficient simply goes down, and at some point, diffusion the diffusion coefficient of atomic diffusion simply is larger than the overshoot coefficient. So atomic diffusion becomes a more efficient process for transporting the elements. So there's not really a cutoff in the overshoot coefficient.
Right. Okay, we can talk about that later, because principally you have a natural cutoff which is related with viscosity, so it's okay. So
okay,
perfect. So there are many other questions. So I think that we can move to the. Okay, we can stop here the presentation and move to the. And first of all, thank you again for the presentation. It was very interesting, and the work is also very interesting. So okay, so I will now try to organize this. Stop first the recording and then organize the breakout rooms.